In all of the examples we looked at so far, we've had the force has been in the direction of motion or opposed to the direction of motion, so it's always been aligned with each other though. So for example, we might have had something, so we've got some kind of block and we've got a force acting on it, and we're looking at a displacement in the same direction as the force, so the displacement's in this, it's aligned, it's parallel to it. Or maybe we're looking at a force applied to a block and the displacement's in the opposite direction from the force. What we're looking now, so these are kind of 1D problems, everything's always aligned with one dimension. So it might be horizontal, might be vertical. What we're starting to look at now is these kind of 2D problems. Now, in this case, the key point is that if something doesn't move, no work is done. So if I have a block and I apply a force to that, so there's a force getting applied to that, there's no work done if that remains stationary, doesn't go anywhere. The only time you're going to get work done is if the block moves. Then it's going to have done some work. Not only that, it has to move in the direction of the force. And so if we go to this problem here, and you can kind of imagine why that's the case. Like imagine if you've got a slope, let me just draw it. You've got a slope with a car on it. And you're pulling that car up the hill with a winch. So it might even be a hand winch. And so the car's attached to that. So you can imagine if you're winding this winch, you might pull the car up a little bit. And you'd have to do a lot of work to do that. So you'd have to do a heap of work maybe to get it to here. But if you then stopped, and if this winch has got a ratchet on it, it's got a catch on it that stops it falling backwards, you don't have to do any more work while it's sitting still. You'd only have to do more work if you're moving it again. So these, in the terms of a definition of work done by a force, you're only doing work if the thing is moving. And so just to keep that car there, if it doesn't have its brakes on, you're going to be applying a force to it. But if you've put a brake on this ratchet, it's still applying that force, but you're not having to do any work in that situation. The only time you're doing work is when there's movement in the direction of the force. So let's have a look at each of these in turn and see what implications that has when we've got kind of 2D problems. Let me just shrink this a little and stick it over here. So we'll call this A. So what we have to do is we still got the case that work done equals F times change in displacement, but we've got the caveat, it has to be in direction of force. So that's one way we can think about it. So it's the displacement in the direction of the force, so it's the component in the direction of the force. Or we can think of it another way. We can say U is F times delta S, so the change in displacement, where you're getting the component of force in direction of displacement. You can do it either way, you'll get the same answer. So for this one here, the obvious way to do that is to find the component of the force. So we've got, I should have just left that really. So this one here, the obvious way to do it is to find the components of this force. It's getting displaced in this direction, and so we need the component of the force in the horizontal direction. Rather than do full free body diagram, I'll just draw the components onto this diagram. And so that's going to be Fx. And I'm not a big fan of doing these 3, 4, 5 forces because you don't often get them in engineering or in engineering problems. But that's the way they've done it. So this book likes to do these 3, 4, 5 rules. So all it means is, so they're just showing this, how, in order to figure out these sides, all you do is whatever the magnitude of this is, you divide it by the number on this side and times it by the number on the side you're interested in. So what we do here is this is 5, so we'll do 500 divided by 5 is 100, and then we're going to times it by 3, so Fx is equal to 300. So the force in the direction of the motion. So let's just write out so people can understand what we're doing. Motion is in x direction, and we should probably just draw on what we're assuming to be our x and y axes. So this y, that's your x, that's your y, sorry, that's your x, This is your y, whatever I'm saying, x, y. And so motion is in the x direction. So we need the force in that direction, the component of force in that direction. And so Fx is equal to, usually you'd be using sine, cos, and tan. They've given us that 3, 4, 5 rule. And so it's going to be 500 divided by 5 times 3 is the one on that side. So it's 300 newtons. And therefore, work done by the force. So the work done by the force is going to be 300. Let's just write it out. The force in the x direction times the change in the x position times delta x, which is just going to be 300 times 2 meters, which is 600 joules. Okay, now in terms of the other definition, the component of that displacement in the direction of force, that's a little trickier, and you wouldn't really use it in this question because it just doesn't make so much intuitive sense. But what you'd be talking about, that's the direction of the force. And so I'd have to split this up into perpendicular components. We're going to have one component of this in this direction of the 2 meters, like so, and another component of the 2 meters, putting it nose to tail at right angles to that. What was that? 53, 54. And so this must be 36. So you're going to have another component of that displacement in this direction, but it's really not making a lot of intuitive sense what you're actually meaning by that. So I wouldn't use that method in this particular example. Much easier to think of, look, I need the component of the force and the direction of the displacement, so calculate the x component of the force because the displacement is in the x direction. Let's have a look at the next one. So this is quite B now. Oops. What have we got this time? So we've got 98.1 newtons downwards, and the block is being displaced in this direction. Now this only has a y component, so it's gravity basically. It would be gravity if this weighed 10 kilos, something like that. So this is your gravity. It doesn't have a component in the x direction. And so therefore, the displacement, you can think of it either way. The component of this force in the direction of the displacement is just equal to 0. So we would have U is equal to F times delta, change in displacement in the direction of the force. And the displacement in the direction of the force for that force is 0. There is no component in the x direction. We could say, in this case, our displacement is in the x direction, so we could say Fx times delta x, and in this case that force in the x direction is 0 times 2 meters, so it's 0 joules. And so this force, another way to think about it is this force couldn't move this in this direction. You know, it can't do any work in that direction. It's not possible for it to move the block in this direction. There must be something else causing it to displace from here to here. The work done by this force is 0. Okay, so that's that one. So when you've got displacement at right angles to the force, there's no work getting done. So when the force is at an angle to the displacement, you just need to find the component of that force in the direction of the displacement. When the force is at right angles to the displacement, you're going to get 0 work. Let's have a look at this next one. This is one where you could probably sensibly do it either way. So either you're, we're saying there's 2 ways to think about this. Either you think about the component of the force in the direction of the displacement, or you think about the component of displacement in the direction of the force. So let's do the first way first. So find using component of force in direction of displacement, same as we did for the first example. So what we're going to have is this is going to have a normal component. It should be about the same again, 52, 53, somewhere in between probably. So we're going to have a component in this direction. Again, this is not a proper free body diagram. we're going to have a component in this direction. We could call that F normal. And we've got a component in this direction. And you would usually call that FT, I guess, the tangential. So now we just have to, we're going to find the component of this force in the direction of the displacement. So it's going to be this one, this FT. But to do that, we just need to know what the angles in here are. And so let's just go through that. So I've drawn on that theta. Let's have a think about this here. So that theta would be, I mean, we could actually calculate what that is. It's just equal to tan to the -1, 3/4, which is equal to 36.87, something like that, 36.87. Now, but we need to figure out, one of these is going to be that angle, just have to figure out what one. So let's just follow it through and see if we can find it. So if I trace that down through here, what we can see here is that angle. We could bring this horizontal here. We'd then have a bit of an F there. So we've got this line here and two parallel lines here and here. So this must also be theta. Therefore, this must be theta. Oh, no, it isn't, sorry. So therefore, what else can we do? So we can draw another horizontal line here. So that's also theta. Theta there. So this here must be 90 minus theta because it's horizontal vertical. So that's 90 minus theta. And the angle between the tangent force and the normal force is also 90 degrees. So we're going to do 90 take away 90 minus theta, which is going to give us theta here. So that's the angle that's theta, this 36 point whatever. Let me just tidy this up again. Okay, so you can think your way through that or do a rough sketch somewhere else. And so we're going to get Ft like so, and we could make a bit of a triangle here. Let's just move that nose to tail, drawing that other one a bit too long. So that would be Ft there. And we'll just sort out the size of this one. Now, so then, if we wanted to kind of use this, what I'll do is I'll just put in that actually rather than stuff around with the 3, 4, 5 rules. And so that angle there is 36.87. So Ft, and we'll actually get the answer out, but anyway, Ft, so the force in the tangential direction, the force heading in the same direction as the displacement. So Ft is just going to be equal to, we've got 100, Ft is opposite, so it's 100 sine theta. Which is equal to 100 sine 36.87, 60 newtons. Just trying to think if that looks okay. Yeah, it looks okay. Looks okay. And so if this was horizontal, looks okay. So therefore, the work done is U is equal to force times change in displacement in the direction, or what we're using this time is the force in the direction of the displacement times delta S, which is going to be, so it's going to be equal to Ft times S, which is equal to 60 times 2, which is equal to 120 joules. However, that's not the only way you can do this. A slightly more logical way to do this, because really probably what we're talking about is gravity. It's a force that's acting directly downwards on this thing. And the easier way to think about this one when it's gravity is just to say that it's just going to be the gravity times the change in the y displacement. So in that case, so let's just say find using component of displacement sorry about the writing, in direction of force. So this time it makes a little bit more sense. What we're going to have is how far down does this thing go, and so it'll be going down this way. That's the direction that the force is in, and then it's going to go along this way, and the total is going to be 2 meters. So use Pythagoras, I mean it's coming to about, I'm not exactly sure where is it getting to for 2 meters? Just beyond that, so it's about here somewhere. Okay, so for this thing to travel 2 meters down this slope, it has to go this much that way, this much that way. We can use the 3-4-5 rule. We could calculate, we know this angle here, so we could use sine, cos, and tan using the angles 36.87. But we can also just go this here. What you're going to do is, this is 2 meters, which is equivalent to 5, so you're going to do 2 divided by 5 times 3. And so what we could write is displacement in direction of force so sorry, I'm just trying to think how I want to say this. So let's also say force is in y direction. And so the displacement in the y direction delta y is equal to 2 divided by 5 times 3, just using that 3-4-5 triangle that they've given us. So 2 divided by 5 times 3, which equals 1.2 meters. 1.2 meters. And so work done is equal to force in the y direction times the change in the y displacement, which is going to be 100 times 1.2, which is 120 joules. So you get the same answer either way. Okay, so in this one, it probably makes more sense to try and find out, look, we're talking about gravity here, and so we want the y displacement of the block. So when the block moves from here down to here, so essentially this block is going to end up here. That'll have moved 2 meters. So this point here has moved 2 meters, so the block has moved 2 meters. So when the block's moved that distance, it's going to have dropped by this value, the component of the displacement in the y direction, and we can calculate either using trig, figure out the angle, just use your normal trig, or you can use the 3-4-5 rule if you're used to using those. You can figure out what that drop is for a displacement down the slope of that distance, and then you times that by the forces in that direction because it's gravity, and therefore you get your work done by gravity. Just checking, in reality, depends what you kind of take as your x and y coordinates. So I'm kind of doing y downwards here because I'm just taking everything as positive. But even if you didn't, even if you took y upwards, that 100, it would be negative 100 times negative 1.2 because the force is going down and the displacement is also down. They're in the same direction. So you'd still end up with a positive answer. So it wouldn't matter. Last one. So this is similar to the first one. It makes more sense to find the component of the force in the direction of travel rather than trying to find the direction of travel in the component of the displacement in the direction of the force is a little bit less, doesn't really mean as much, it's not so intuitive. And so let's just say D. So motion is in x direction. And let's just show our x and y axes, just show people what we're assuming here. So this is x, this is y. So the component of force in the x direction, Fx, is equal to, so again we could calculate that little angle. if you're not sure what you're doing with the 3, 4, 5, but otherwise that 100, we can divide it by 5, and we want the component in the x direction, which is the 4 this time. So it's just going to be 100 divided by 5 times 4, which is equal to 100 divided by 5, 20 times 4, which is equal to 80 newtons, but it's in the negative direction. So it's negative 80 newtons. So we're taking x positive this way, so this is negative 80 newtons. Then we're going to get the work done as force in the direction of displacement times the displacement. In this case, it's Fx times delta x, the change in x, which is equal to minus 80, but the displacement is positive. It's positive 2 meters times 2, so it's minus 160 joules. Okay, so this time it's negative work, so this is work getting done against this force. Of course, this force is doing negative work. And again, either there's another force working here that's applying this, moving it this way, or it might be that this thing has an initial velocity and this force is slowing the block down, something like that. But anyway, energy is getting taken away from this, or this is countering some other force that's acting. Okay, that's it.